Hello, AP Stat scholars. Here is linear transformations of random variables, 6.2a. So we're going to start with an example. Dolores sells cars at a local dealership. The distribution is X is the number of cars sold for Dolores per month. And you can see if she sells 0 cars at a 0.3 probability, 1 car at 0.4, 2 at 0.2, and 3 at 0.1. So pause the tape for a moment so you can practice finding the mean, variance, and standard deviation of this distribution. Okay, so to find the mean, we use the same formula we've been using, 0 times 0.3 plus 1 times 0.4, etc., and we get 1.1. So the mean, or mu of x, equals 1.1. That's our weighted average. So how we interpret that is, on average, Dolores sells 1.1 cars per month. And now we're going to find the variance. So we use our formula for the variance, and we get 0.89 as our variance. So sigma of x squared is equal to 0.89. Now remember, to find the standard deviation, we take the square root of the variance. So we end up with the square root of 0.89 is 0.9433, etc. So we're going to go ahead and round that to 0.94. So the standard deviation of x is 0.94. Our interpretation of that is the number of cars Dolores sells per month varies from the mean by about 0.94 cars per month. Okay, here's a new situation. This time we're looking at Dolores's paycheck. So suppose Dolores makes $800 for every car that she sells. Now we have a new distribution, call it y, and it's based upon how many cars she sells. So the relationship between y and x, how many cars she sells, is 800 times x. So you'll notice if she sells 0 cars, she gets $0 on her paycheck. But if she sells 1 car, she gets $800, 2 cars, $1,600, 3 cars, $2,400. But the probabilities remain the same because the probabilities of selling that many cars still remains the same as it was in the table for x. So now pause the tape for a moment here and take your time to find the mean of this new distribution. After you found the mean of the new distribution, try to look at the mean of the original and see if you can find a relationship between those two values. So the new mean is 880. And if you'll notice, the new mean is actually 800 times the original mean of 1.1. So we find that relationship of multiplying 800 times x also stands true for the relationship between the means. But something interesting happens when you find the variance. Well, I find the variance, I get this whopping number, 569,600. Well, that might have been a surprise for you, because if you multiply the variance of the original times 800, you will not get this number. What you might not have noticed, because it's a little harder of a relationship to see, however, is if I actually square the 800 and multiply it times the variance, I do end up with a correct variance for the new distribution. So what that tells me is that squared relationship and that formula that happens when we do variance holds true for the multiplying of the constant as well. Then to find the standard deviation, I go ahead and take the square root of 569,600, and I get 754.7. Okay, so now we need to see, what is this relationship? So we notice that when we multiply every value in a distribution by some number b, the mean is multiplied by b, but the variance is multiplied by b squared. So that's an important relationship, and we're going to write that down later. Here's a new scenario. So suppose Dolores gets a bonus every month. If she replaces one set of brakes, she gets $200. So now we have a new distribution z, which includes how many cars she sells plus that extra bonus of $200. So the relationship between z and y, her paycheck, is y plus $200. So now her paycheck reflects that. So instead of $0 for selling 0 cars, she still gets $200 for doing the brakes on a car. And then she gets 1,000 now instead of 800, and 1,800, 2,600. So I added $200 to each of the values from Y. So pause for a second and think about what that might do to the mean and the variance. All right, now calculate them on your own if you haven't already and see what you get. You should have gotten that the mean of Y is 1,080. So what is the relationship between that and the previous mean of 880? Hopefully you see that it is added by 200. So 880 plus 200 is 1,080. But something weird happens when you do the variance. The variance remains the same. There's no change in the variance, and therefore the standard deviation remains the same as well. So when I added a constant to the random variable, it changed the mean. I added the same amount to the mean, but the variance and standard deviation, or in other words, the spread of the distribution, is unchanged. So why might that be? So looking at just a regular normal curve, think about how spread out this is. If I added a value to each and every value in this graph, what would it do to the graph? Envision in your head what my new graph would look like. That's right, if I added a constant value, the shape of the red graph does not change at all, and the blue graph is just basically that red graph moved over by the amount I added to it. So since variance and standard deviation measure how spread out your data is, nothing changes when I add a constant to it because the spread remains the same, simply the mean moves over by that amount. Okay, so what we learned now is adding a constant to a distribution means that the mean, or average, is increased by that same constant, and the variance is not affected at all. It's the same as before. Okay, so now we have some general rules for transforming random variables. If you know the mean of the original value, but you have a new value where you added a constant a and you multiplied by a constant b, then the new mean is going to be added by that same constant and multiplied by that same constant. So it shares that same relationship as far as the mean goes. But as far as variance goes, remember adding a constant a has no effect whatsoever on the variance. However, multiplying by a constant b means the variance is now multiplied by b to the second power. So your new variance is b squared times the old variance of sigma squared. And I'm ending on a question. Are monsters good at math? Not unless you count Dracula.